Pick up a penny. Look at it. That brown disk in your hand contains more technological sophistication than the entire Roman Empire ever produced in metal, and Romans would have killed for it. Not the penny, the copper. They called copper aziz, used it for everything, built their economy around it. Copper was their gold, which raises an uncomfortable question. What exactly makes gold gold? Not the color. Cesium is golden. Not the weight. Osmisium is denser. Not the rarity. Not really, and I'll show you exactly why that statement is more precise than it sounds. What makes gold gold is a specific accident of nuclear physics combined with a specific accident of stellar evolution combined with a specific accident of how gravity sorts molten planets. Strip away the accidents and you have an element that by any rational accounting should cost about as much as copper. Let me show you how this falls apart from first principles. Start with the periodic table. Not the poster on a classroom wall, but what it actually represents. Every element is defined by how many protons are jammed into its nucleus. Hydrogen 1, carbon 6, gold 79. The number of protons determines everything. The electron configuration, the chemical behavior, the melting point, whether it corrodes in air, whether it dissolves in acid. You want gold? You need exactly 79 protons sitting together in a nucleus. No more, no less. Now here's the problem. Protons are positively charged. Positive charges repel each other with a force that scales as the inverse square of the distance between them. Pack 79 protons into a nucleus, roughly 10 to the minus 14 meters across, and the electromagnetic repulsion trying to blow that nucleus apart is staggering, something on the order of thousands of newtons operating at nuclear distances. The only thing holding it together is the strong nuclear force, which operates at even shorter range and wins the contest, barely, for nuclei up to a certain size. Building a nucleus with 79 protons requires adding protons and neutrons under extremely specific conditions where the strong force can operate fast enough to overcome the electromagnetic repulsion before the nucleus flies apart. You cannot do this slowly. You cannot do this at normal stellar temperatures. The core of our sun reaches about 15 million degrees Celsius, and at those temperatures you can fuse hydrogen into helium efficiently. You can, with a massive enough star, eventually reach conditions that fuse silicon into iron. Iron has 26 protons, less than half of gold's 79. Getting past iron requires what physicists call the raw process, rapid neutron capture. You slam neutrons into existing nuclei so fast that the nucleus doesn't have time to beta decay before the next neutron arrives. The nucleus absorbs neutron after neutron, getting heavier and heavier, and then decays into progressively more proton-rich configurations. Do this fast enough, with enough neutron flux for long enough, and you build up elements all the way to uranium and beyond. The only place in the observable universe where we've confirmed this happens is a kilonova, the collision of two neutron stars. On August 17, 2017, at 12:41 UTC, gravitational wave detectors in the United States and Italy simultaneously registered a signal lasting approximately 100 seconds. Two neutron stars, each about 1.4 times the mass of the Sun, but compressed into objects roughly 20 kilometers across, denser than anything except a black hole, had been spiraling toward each other for billions of years, and finally merged. The collision released more energy in 2 seconds than our Sun will produce in its entire 10 billion year lifetime, and telescopes watching the aftermath saw something specific in the light spectra, the unmistakable signature of freshly synthesized heavy elements. The event, called AT 2017 GFO, is estimated to have produced somewhere between 3 and 13 Earth masses of gold in approximately 2 seconds. Every gold atom in existence was made this way. Every ring, every coin, every bar in every vault. The gold sitting in Fort Knox, 4,580 metric tons of it, was forged in a stellar catastrophe. The idea that it's precious because it's rare is getting the causation backwards. It's rare here in accessible deposits because of the specific geological accident of how Earth formed and differentiated. The universe, if you could mine it, is not running low. Here's where I want to push on your intuitions about scarcity, because I think there's a confusion buried in how we use the word. There are two completely different kinds of scarcity. The first kind is physical. The thing requires specific arrangements of matter and energy that nature only produces rarely. Antimatter is physically scarce. It annihilates on contact with regular matter. The universe produces very little of it. and creating it artificially costs roughly $62 trillion per gram at current energy prices. You're not going to manufacture your way out of antimatter scarcity. The second kind of scarcity is what I'd call positional. The thing exists abundantly, but most of it is inaccessible, and the cost of access defines the effective supply. Gold is positional scarcity, dressed up in the language of physical scarcity, and conflating these two things is responsible for an enormous amount of confused thinking about value. Consider the numbers. The Earth's oceans contain an estimated 20 million metric tons of dissolved gold. 20 million. All of human civilization has ever extracted 244,000 metric tons from mines. The oceans contain roughly 80 times that in solution right now, stirred into the water that covers 71% of the planet's surface. The gold is not gone. It's not in some other galaxy. It's dissolved at a concentration of about 13 parts per trillion in water you could drink. Fritz Haber, the man who invented the process for pulling nitrogen from the air to make fertilizer, which currently feeds roughly half of all living humans, spent years after World War I trying to extract this oceanic gold. Germany owed enormous war reparations. Haber thought he could pay them by mining the sea. His measurements suggested the concentration was higher than it actually was, and when he got better data, the economics collapsed. At 13 parts per trillion, you'd need to process roughly 80 billion liters of seawater to extract a single kilogram of gold. The energy cost alone, pumping and processing that volume of water, would exceed the value of the gold recovered at any realistic price. He failed, but the gold is still there. And then there are the asteroids. The asteroid 16 Psyche orbits the Sun in the belt between Mars and Jupiter. It's roughly 220 kilometers across, smaller than some moons, large enough to qualify as a major asteroid. Psyche appears to be largely metallic, possibly the exposed iron-nickel core of a protoplanet that lost its rocky mantle through ancient collisions. NASA launched a spacecraft toward it in 2023. It should arrive in 2029. Early estimates, which have since been revised downward, suggested Psyche's total metal content could be valued at something like $10,000 quadrillion at current market prices. The revised estimates are lower, still enormous. More importantly, Psyche is one asteroid. There are roughly 1.1 to 1.9 million asteroids in the main belt, larger than 1 kilometer. A meaningful fraction are metallic. The gold sitting in the asteroid belt almost certainly dwarfs everything humanity has ever mined. None of this gold is accessible cheaply today. That's real. The energy cost of space mining is enormous. Ocean extraction doesn't pencil out. Deep-sea floor gold deposits require technology we haven't deployed at scale. The effective scarcity is genuine. You can't just go get it. But effective scarcity and fundamental scarcity are different things, and the price of gold is built on a story about fundamental scarcity that the physics does not support. Let me show you what actually drives the price, because it's more interesting than there's not much of it. Gold has a chemical property, rooted in quantum mechanics, that almost nothing else on the periodic table shares at room temperature. It barely reacts with anything. You can leave a gold bar on a table for 10,000 years, and it will look exactly the same. This happens because gold's electrons, particularly the outermost 6s electrons, are pulled unusually close to the nucleus by relativistic effects. When electrons move at speeds approaching a significant fraction of the speed of light, as the inner electrons of heavy atoms do, their effective mass increases, as Einstein's special relativity requires, and their orbitals contract. This contraction in the inner shells propagates outward, affecting the 6s electrons, making them less available for chemical bonding. Gold is stable because it's quantum mechanically lazy. That stability has genuine value for certain applications. Electronics, because connections that don't corrode are connections that stay reliable. Certain medical implants, because inertness inside a human body matters. Catalysis, where gold nanoparticles turn out to be surprisingly active for specific reactions despite bulk gold's sluggishness. But the premium that stability commands in industrial applications is nothing like what gold actually costs. Platinum has comparable stability. Iridium is more stable. Palladium has most of gold's useful industrial properties. The price of gold in your ring is not tracking the quantum mechanical laziness of the 6s electrons. It's tracking something else. What it's tracking is roughly 5,000 years of compounding cultural momentum. Somewhere around 3000 BCE, somebody in Mesopotamia or Egypt made a decision, maybe deliberately, maybe by gradual consensus, to use gold as a store of value. They didn't know about neutron stars. They knew that gold didn't rust, that it was dense and difficult to fake, that it was rare enough in accessible deposits, that it couldn't be easily manufactured, and that it was workable enough to be fashioned into standardized shapes. Those four properties together solved the coordination problem. How do you trade across time and distance with someone you don't trust? You find something both parties recognize that can't be easily faked or inflated, and that will still be worth something when you get to the other end of the journey. Gold worked. It worked so well for so long that the belief in its value became self-reinforcing. Every generation that grew up with gold as a store of value had good reason to accept it as a store of value because everyone around them accepted it. The price today reflects not just the geological constraints on supply, which are real, even if exaggerated, but the accumulated weight of every civilization that ever used gold as money. That's an almost impossible thing to dislodge, and it's worth being honest about. The value of gold is partly a stable collective hallucination, but a hallucination that 8 billion people share is for practical purposes indistinguishable from reality. Here's the honest summary. Gold is rare in the way that a specific parking spot is rare. The spot is genuinely occupied, genuinely unavailable, and if you want it, you have to wait or pay. But the underlying resource, places to put a car, is not fundamentally scarce. What you're paying for is location. With gold, you're paying for accessibility, concentration, and the weight of accumulated human belief. The first two are geological facts. The last one is a story. The story might be worth more than the metal. Throughout history, the ability to participate in the gold consensus, to hold a thing that Egyptians and Romans and medieval merchants, 20th century central banks all recognized as valuable, has been a kind of civilizational passport. You could cross any border, survive any government, outlast any inflation, as long as you were holding something the next person in the next century would want. That's genuinely powerful. That's not nothing. But the next time someone tells you gold is precious because it's rare, ask them, rare compared to what? Rare where? On Earth's surface, inaccessible deposits, yes, genuinely rare, genuinely constrained, in the oceans, in the crust, in the core, in the asteroid belt, in the debris fields of dead star collisions scattered across the galaxy. No, what's rare is the alignment of circumstances that puts it somewhere you can reach it. The universe makes gold in industrial quantities every time two neutron stars find each other after billions of years of drifting. It's violent, it's spectacular, and it happens often enough to scatter gold across every solar system in the galaxy. The precious metal in your pocket is just the local delivery. What we've decided it's worth is a different story entirely, and that one we're still writing.